Okay, welcome to our tutorial on permission blockchains. So could you please play the first part of the tutorial?
Hello and welcome to our tutorial on permissioned blockchains. We're going to cover various aspects of blockchains, properties, techniques, and applications. This is, I want to emphasize, on permissioned blockchains and not permissionless blockchains. I will explain briefly at the very beginning the difference, but just so that you know from now. This is a tutorial that will be presented by Mohammed Amiri, who was a student of Divi Agrawal and myself. All of us are presenting. We come from UC Santa Barbara. Mohammed was a student at UCSB and now is graduated and is a postdoc at University of Pennsylvania. So you've all heard about blockchains. And the most common context for people talking about blockchains is in the context of cryptocurrencies. So what's the idea of these cryptocurrencies? Well, if you think of how we normally interact with each other financially, there is a bank, as you see here, which is an entity that we all trust. We put our money in the bank, and then if I want to give Divi a certain amount of money, I write him a check and he goes to his bank, I go to my bank, and the two banks transact with each other, and the transaction is performed where the money that the $50 that I want to give to Divi are transferred from my account to his account. That's a traditional way of looking at transactions and banks. What cryptocurrencies do, and this idea was basically developed and innovated initially in Bitcoin, is that you replace this trusted bank entity with a peer-to-peer distributed system where everybody keeps track of everything that is happening. So instead of having one bank that has all the information, you replicate all the transactions that are occurring on various different entities, and each of them keeps track of everything that is happening. So in a way, you have complete replication of the entire history of all the transactions that have been occurring in the system. So a blockchain is basically a ledger or a log of all the operations that have happened, and it is replicated for fault tolerance and for performance reasons. And in general, in a cryptocurrency system, you'll have all these different entities that are called miners, and they keep trying to solve a problem. And once they solve it, if they succeed, they become the winners. They can add the next block to the blockchain, and they distribute it among everybody in the system. So that's in a permissionless blockchain system. One winner is the leader, is able to add the additional block at the end of the blockchain, while the others just adhere to what was given to them and add it to their block, and then they start again the whole process. So the question is, does this blockchain data structure, this kind of this ledger that has blocks after the other connected with each other, which has several advantages? It gives us a provenance, it gives us the history of everything, it gives us a trace of how we evolved and how the current state was reached. Are there other applications other than cryptocurrencies? And turns out, surprise, surprise, there are lots of applications. In particular, there are many applications, and I'll just use this example, a supply chain in the real world, where it's used, for example, to keep track of fish and the production of fish, the fishing of the fish, the marketing of the fish, the delivery of the fish to the fish market, and eventually to the table where you're going to eat it. And what you're interested in is to know the trace of the food that you're eating through the entire system so that you can verify that it is fresh and is good. And blockchains have been used in this context. So you can use a seafood supply chain in a blockchain manner. When a fish is caught, you use RFIDs, you use sensors, IoT-enabled sensors to keep track of what's happening. Sensors continuously transmit location and time information, which is integrated into the blockchain to keep track of what's happening. So the blockchain system tracks possession, the changes that are happening throughout the system. So if, for example, eventually the food arrives at your table and it is not fresh, then you can identify whether the delay in the processing, in the delivery happened at the fisherman's side or during the processing or during the transportation process. So there's a tracking of all the various times that have been happening throughout the history of this. So the buyer can access a comprehensive ledger or record of the fish's provenance. This is very interesting and useful in many various different contexts. So in general, we divide blockchains into two types of blockchains. What you have on the left is blockchains where anybody can participate without a specific physical identity and without knowing how many entities are involved in the system. This is typically what has been occurring in the context of cryptocurrencies. On your right-hand side, you have another system where the participants are known, are finite, are well identified from the very beginning, and they decide they want to work with each other. They might not trust each other, but they're going to work with each other. So we have permissionless or public or open blockchains, and we have permissioned blockchains. This tutorial is going to focus on permissioned blockchains. We are not going to be discussing permissionless blockchains anymore. We'll just focus on permissioned blockchains. So a permissioned blockchain consists of a set of known identified nodes that might not necessarily trust each other. So this is the big thing that is happening when we bring these blockchains into the database world. Is in the database world, typically we assume that the storage devices are trustworthy, so they can crash, they might fail, but we don't assume maliciousness. However, in a blockchain world, you might have the fisherman and the transportation system do not necessarily trust each other. And it might be to their inherent interest to actually fool the system so as to get away with maybe delays that were unpredictable or whatever. So we have a set of known identified entities, nodes, that need to agree on this one data structure, which is the log, this blockchain. So you need to reach consensus among the various copies. This blockchain, this ledger, is being replicated on lots of different nodes. In a permissioned environment, they are well known, but they don't trust each other, so we need consensus among all of them. We need agreement among all of them, and typically what is used is practical Byzantine fault tolerance, and I will describe this briefly for you in a few minutes. This is in contrast, just to remind you, of permissionless blockchains, where the nodes are unknown and, of course, not trusted. In that case, we need to reach consensus, and the traditional terminology for that is that you do mining. In a mining system, you end up replacing the communication that takes place in a Byzantine agreement protocol with computation. You try to solve this puzzle, and the puzzle typically is a difficult puzzle, so difficult in the sense that it takes a long time to solve it. You have to explore an entire space to solve the puzzle, and so it's exponential in complexity. You don't have any shortcuts, and as a result, it takes a long time. Typically, in Bitcoin, for example, it takes about 10 minutes. One winner is the one who is going to be able to add the block to the blockchain. Now, let me just highlight some of the unique features and the reasons why people use blockchains. They are very useful because they provide provenance. For every asset, you know the entire history of it, you know where it has been and what has happened throughout its lifetime. It's immutable. Once a block is added, it cannot be ordered. We have a copy of it on all these various sites, and it cannot be ordered, so it is immutable. It provides us with persistence. It's fault tolerant because, as you saw, every copy of the ledger is stored on many different sites, so it continues to operate even if nodes fail or act maliciously. Since every party has access to the blockchain, it is transparent. Any party can audit all the contents of the blocks and determine whether everything is consistent or not. And finally, because the system is decentralized, the data is complete, consistent, is available in a timely manner, is accurate, and widely available. Before delving into more details, let's just ascertain what is actually a blockchain ledger. And this actually applies to more or less both permissioned or permissionless blockchains. So a blockchain ledger is an append-only structure. You have blocks and they are connected by pointers, and it's always appended at the very end. So at the very end. So you always are adding to the very end of it. Each block contains a batch of transactions, and the order of transaction execution is captured by chaining the blocks together. So this block is before, and the transactions in it are before the following one, and so on. Now the order is captured with these pointers, and to make sure that the contents are tamper-free and nobody, because we are storing these ledgers on untrusted infrastructure, we need to make sure that they will not tamper with it. So the trick that is done in blockchains is, in addition to a pointer, you actually include a hash of the previous block. This will guarantee that the blockchain is tamper-free. This is a cryptographic hash, which is very difficult to break. It's basically a SHA-256. The blockchain is stored in a large distributed system, basically a system on nodes that are in an asynchronous system. So here we have a bunch of nodes, and they are scattered potentially across the globe. The nodes maintain the state of the system, which is updated by executing transactions. Transactions basically read and write operations, data that is stored at these nodes. The blockchain ledger that we just saw on the last slide is replicated on all nodes. So it is fully replicated. Every node in the system has a copy of this blockchain, and hence can track everything that is happening in it. Nodes establish consensus to agree on a unique order. In particular, they need to add an additional block at the end of the blockchain, and we have to make sure that all of them have a consistent, unique order on all the blocks. So consensus is executed, and when a node becomes the leader, it needs to validate that all the new transactions in this block are consistent. Permissioned blockchains use traditional consensus protocols, unlike permissionless, which uses mining. So depending on the underlying assumption about the failure model for the nodes in the system, we might use, if it's crash, if we assume that they are crash, then we use Paxos. The more common assumption is that the nodes might be malicious and hence might act in a Byzantine way, and in that case we use PBFT. So what is the consensus problem? I've been talking about it. It's a set of nodes, distributed nodes, meaning they can only update data by communication, they need to agree with each other on a single value. In a blockchain, they need to agree on the next block that is going to be added to the blockchain. So before we get into the depths of permissioned blockchains and the various applications, I'm going to just give a high-level description so that you are aware of the foundations of the protocols that are used in consensus in distributed systems. This will not take very long. The original proposal was for an asynchronous system, distributed system, and in the context of crash failures. So here I'm starting with a simple protocol for crash. So nodes are trustworthy. Paxos was proposed by Lamport, and what is typically used is a variation of it, which is used usually in distributed systems and especially in permission blockchain systems. It's called multi-Paxos. Paxos in general and multi-Paxos in particular have the notion that are leader-based. So there's one node that is going to be the leader of the system. In this case, it's node 0, and it has been elected. So there is an election phase that happens first. But in the steady state, you have a node that is assumed to be the leader. The clients typically know who the leader is. So in this case, we have one node, which is a client, and we have an object that is replicated, say, on 3 different sites, node 0, node 1, and node 2, and time goes from left to right, and we can tolerate some number of failures. In this case, I'm assuming that node 2 is the one that is going to fail. So a request comes, a client wants to, let's say, add a block to a blockchain. So what it does is it goes to the leader, whoever it thinks the leader is. If it's wrong, the message is forwarded to the leader. And the leader now, it knows it's the leader. It's going to make sure that this value is replicated on enough copies, on enough sites to make sure that it is fault tolerant. So what it does is 2 phases of communication, back and forth, or 1 round, where it sends out an accept message telling the different nodes in the system. In this case, it's going to call the 2 other nodes and itself. So it sends an accept message with the new value. Once it gets back an answer telling it that a majority, in this case 0 and 1, have the new value, have accepted this value, then you know that it is fault tolerant, it's going to be committed. So it commits it, and it replies to the client saying, yes, your value has been committed, and informs everybody else that the value now is committed. Notice that at the end of the accepted phase, only the leader knows that the value has been accepted. The other nodes, in particular node 1, does not know yet. It just has answered back, but it doesn't know if a majority have already accepted it or not. So the leader has both the responsibility of committing the value, replying to the client, and updating the other nodes in the system to inform them of the new value that has been committed. So this is basically multi-Paxos. To tolerate F nodes, F failures, F crash failures, you typically need to have quorums, and the quorum is typically a majority. In general, it is F+1, and any 2 quorums must have an intersection of at least 1. So if you want to tolerate F failures, you typically have a network of 2 F+1 to do anything, you need to get agreement or a quorum from a majority, F+1, and you'll notice that the intersection between any two quorums is 1. The protocol has two phases. Once the leader is elected, all it has to do is it has to send accept and wait back for accepted messages. So the complexity is big O of n. It's linear in the number of nodes that are in the system. So this is basically a high-level description of Paxos. Paxos tolerates crash failures. However, as I indicated earlier, we are interested here in tolerating malicious failures, in tolerating nodes that are not trustworthy, nodes where the response to a message might deviate from what the protocol is describing. So the foundational protocol for that is what's known as Practical Byzantine Fault Tolerance. It was developed by Castro and Liskov in 1999, as you notice, almost just briefly after Lamport's Paxos protocol. It is also for asynchronous systems. It is also based on a notion of a leader who dominates and facilitates the updating of values. However, it is designed for malicious failures. To tolerate malicious failures, and I'll tell you now, you need to have at least, you can tolerate at most 1/3. So F is at most 1/3 of the number of processes. So here I have an example. Again, these timelines go from left to right. We have a client with a new value, and to tolerate one failure, in this case node 3, who might not only crash, but might actually lie. So it might, in the previous example, always the crashed site never sent any messages. However, now the failed site might send messages, but they might be incorrect. So we have at most one failed site, and we'll have 3 other processes. So with 4 processes, you can tolerate 1 failure. Again, the client sends a request with a new value, let's say the block in the blockchain, to the leader. What the leader does is it sends what's called a pre-prepare phase, where it sends this new value to all processes in the system. So it sends it to the other sites, as you see. What can happen now is that the node 0 might be malicious. Node processes in the system are not aware of this. So as a result, there has to be agreement on the value that it's sent. As a result, we cannot continue as we did with Paxos immediately to a commitment. Instead, the different sites in the system exchange with each other the values that they received. So the prepare phase is when each site sends to everybody else. So n² messages here are being sent to everybody else. These are sent to each other to validate what value they received. Once every site has received the prepare phase, they can again exchange messages with each other, so n² again, to commit the value. If at the very end of the commit phase, a node receives consistently all values that are, a quorum of values that are consistent with each other, then the value is committed. So you need to get here from a quorum, and the quorum has to be consistent in the value that it's sending to each other. If nodes receive this, then what they do is they respond back to the client with the value and the reply with the value that they committed, and the client needs to get at least F+1 consistent messages with each other to tolerate the potential of F failure. So if you get F+1, you know that they have the same value, that they are adding the same block, let's say, then it must be consistent with each other, because you can't have more than F malicious failures. So in this case, we have quorums, and the quorums are 2F. So to tolerate F, I need to have quorums of size 2f plus 1 and the network of size 3f plus 1. Or put it in other ways, if I have n processes, a third of them need to be, I can tolerate at most a third of them failing, and I need quorums that are 2/3 of size. Why do I need 2/3 size quorums? Because as a result, if I have the intersection of two different quorums, each of them of size 2f plus 1 will result in an intersection of f plus 1, and if all f plus 1 values are identical, the returned values are identical, then we know that the value is consistent, because is correct, because out of those f plus 1 there can be at most f failures, so there's one of them that is correct, that is not lying, and since they all agree on the same value, then we know that that value is the value, and that's the correct value. What you'll notice is that unlike with Paxos, we now have 3 phases of communication, and there's an explosion in the number of messages. Instead of a linear number of messages in the number of sites that we have in the system, here we have order n square. And of course, the quorums have increased in size. So Paxos is a foundational protocol that is used to reach agreement and consensus in distributed systems. It's the foundation also for practical Byzantine fault tolerance, and PBFT is the foundational protocol that is used in most blockchain systems, permissioned blockchain systems that need consensus. Typically, they assume that you don't trust each other, so they use PBFT. Sometimes we develop a permissioned blockchain system in a system where the nodes actually trust each other, and in that case we can actually have the easier case where we can use Paxos, and as you saw, it has several advantages, both in terms of latency and in terms of throughput and communication. Latency, notice, is a direct function of the number of phases that you are executing the protocol. Paxos needs 2 phases, while here we need 3 phases of communication. Okay, so this was just so that we are not going to delve more into details about these protocols. We are going to use them, but I wanted to make sure that you are comfortable with and are aware of the foundations of these consensus protocols. So now we want to use permissioned blockchains in various applications to help us to facilitate various applications. So for example, if I would like to use blockchains in a financial environment. Why would I like to do this? Because it gives me the provenance of all the various transactions that are happening in the system. So it's a very powerful, it gives me a trace of everything that has happened in the system. However, the challenge with financial systems is performance. Typically with Visa, with credit cards, with banking, you have tens, if not hundreds of thousands of transactions being processed in 1 second. Blockchain systems are much slower. Their performance, their throughput is much less than this. For example, if I was in a permission-less environment, our performance is actually, as I mentioned, it takes about 10 minutes to solve the puzzle. So as a result, you have 7 to 10 transactions per second being executed, while in the real world, we need a lot more performance, even a lot better performance. Even if we change to permissioned environments, as you saw, the permissioned blockchains require consensus, and if you are assuming Byzantine fault, if we're going to use PBFT, it requires 3 rounds of communication. As a result, the performance is actually not as good as the strong database systems that you have all been developing and working on. We've been working really hard in the last 30 or 40 years to radically improve the performance, the throughput of transactions in commercial database systems. Using permissioned blockchain systems is not competing enough. So we're going to explore ways in which this can be achieved. Another environment that I've mentioned earlier is the supply chain environment, where you have various entities that do not trust each other and who want to work with each other. Maybe the performance isn't a big issue for them. However, in this case, we have a problem of confidentiality. In a blockchain system, as you saw, the blockchain is a series of blocks that refer to everything that has been happening in the system. The whole notion of a blockchain is to be able to see the provenance of all the transactions that are occurring. As a result, there is a lack of privacy. There's a lack of confidentiality. And this is a challenge in an environment where we want to support different entities that might want to hide some information from each other while sharing other information. Why not use blockchains in large-scale database systems? As I've alluded, we would like to do this, and in large-scale systems, we have very good performance. The challenge here is that it doesn't scale. The way blockchain systems, permission blockchain systems, did not support scalability, and we need to inject ways in which we can support scalability. Finally, a new application that has arisen is to use blockchains in crowdsourcing environment, where we have a provider like Uber and then drivers, and they need to work with each other. In such environments, we need to verify that everything that every entity is doing is actually adheres to the rules and regulations of the system, whether it's labor laws or healthcare regulations, etc. So I would like to inject into my blockchain tools that will allow verifiability. What we are going to do in the rest of this tutorial is to explore these different aspects. So we're going to look at performance, and we're going to explore various different ways in which performance can be improved using different techniques that are optimistic, pessimistic, using notions that are very familiar to database people to improve the performance. We will explore confidentiality issues, whether we can split the blockchain into different components that are view-based and seen by different entities but not by others, or to use cryptographic techniques. We're going to explore scalability. So as I described it, we have a ledger in a blockchain system. Maybe we might want to shard this blockchain ledger. So as a result, improve performance. And finally, verifiability, how to ensure how to be able to verify certain aspects. For example, we could use zero-knowledge proofs or tokens. So overall, what we're going to try and do is to show you how various techniques that some of you might be familiar with from a database world, to apply them in an environment with permissioned blockchains. I'm going to stop here, we'll take a break, and then we'll continue around this cycle. See you later. Bye. In this section, we are going to start exploring performance issues with blockchains, and we will investigate various approaches in which blockchain systems have tried to improve performance. A lot of the ideas actually will sound very familiar to many of you database people who have worked in infrastructure, because performance depends a lot on the amount of concurrency, parallelism that we can achieve while accessing data. And as you know, there are traditionally pessimistic approaches and optimistic approaches. So in the pessimistic approach, you lock stuff first. For example, if I'm using two-phase locking, so you ensure the order in which transactions are going to be executed before you execute a transaction. Once I've obtained all my locks, I know that the execution will be correct and serializable, consistent, and all of that. On the other hand, we have optimistic approaches where you optimistically assume that there is no conflicts. You execute the operations and then verify, validate later on that conflicts did not occur that are going to violate the order that in which the execution was made. So the ordering is done afterwards. So what we're going to see here is how the same philosophy was actually implemented in various permission blockchain systems. So we have two things we have to worry about: the order in which operations are executed, the order without executing them, and then the execution. So those are the two main phases. You can order first, i.e. a pessimistic approach, and then execute. And there are many examples of this, for example, Tendermint, Quorum, Chain Core, multi-chain, etc. Or there is the optimistic approach where you execute first and then order and validate that the order that you got is consistent with the execution order. Finally, there is an approach which is also pessimistic, which is the order parallel execute. And in that case, you order, but you extract enough information about the relationship between conflicting operations so that when you execute them, you can execute them in parallel. And this is the approach which was used in Par blockchain. So let us start with the order execute. In this case, we have a set of clients, a set of orders, and a set of executioners. The blockchain is replicated among the executioners based on whatever criteria you might have. So you have different applications, you have a supply chain, etc. You might have different reasons for having a different number of executioners. The order is independent, and that depends on your underlying failure model. If we're going to assume malicious failures, then we at least require a 3f plus 1. So if f is equal to 1, then I need 4 orders to overcome potentially malicious behavior of one node. So you have to know the underlying assumptions about the system. Clients issue transactions. Each time a transaction is issued, it is sent to the orders to find an order in which consensus is maintained, is achieved to order these various transactions. Once you have a block or enough transactions, depending on a notion of epochs or a notion of the size of each block and how many transactions are going to fit into a block, you take this block and it's been ordered, you send it to the executioners. Now, what do the executioners go? They go sequentially through each of these transactions that are in the block and execute them one at a time. Once they are done, we are finished. Of course, the challenge here is that you are executing the transactions sequentially, one at a time. And this was kind of the whole reason why we moved from serial execution in a regular database system. We developed concurrency control protocols to achieve serializable behavior. So, but this is the basic model for the order execute. And a good example of this is Tendermint. And Tendermint uses PBFT, so Byzantine fault tolerance. Now, you have a lot of nodes in the system, so you want to ascertain or to determine who are going to be the orders. So they use a notion which is actually borrowed from the permissionless world, which is called proof of stake. In proof of stake, a node can act as a miner or validating transactions according to the amount of wealth that it has, so according to the amount of coins that it has. And when a node participates in a consensus protocol, it takes these coins and deposits them in a bond. So this kind of restricts that I cannot keep using this amount of money all over again, and the orders become the same. An order then has voting power that corresponds to amount of bonded coins that it has. So if I'm very rich, then I have a lot of power in my voting assets during this particular ordering behavior. The protocol is actually PBFT, so it goes through the cycle. I will not go through this flow chart that indicates things, but basically you need to acquire quorums, and because this is PBFT, you need 2/3 majority, and the voting is not based on one side being equal to 1, but rather one side is equal to the amount of bonded coins that it has. And whether you are in the first phase or the second phase of PBFT, you remember from when I described it at the beginning, you wait for a majority of pre-votes or a majority of pre-commits to eventually commit. A very other extreme example of a system is Hyperledger Fabric. This is a well-known, and we'll be using this Hyperledger Fabric often throughout this tutorial. It's an open source resulting from a consortium of different companies, including IBM, Intel, SAP, and several others. I'm going to illustrate at a high level how they take an optimistic approach. So they're going to execute first and then order and validate that the order is consistent with this execution order. And the basic operation we have is read and write operation. So we basically are looking for read and write conflicts. What's interesting here is that Hyperledger Fabric supports non-deterministic execution. So you might have code that is non-deterministic and it still supports it. As we will see later, other systems assume that the execution must be deterministic. So in this case, I'll illustrate things using, again, our 3 different types of nodes. We have clients. They represent applications, and they're going to issue transactions that need to be executed. There are going to be endorsers, and those are execute the transactions and then validate that the transactions were actually ordered in the same and resulted in the same results as was the execution. The endorsers maintain the blockchain ledger, and each application has its own set of endorsers. So we'll have different applications, each of them with its own set of endorsers. And they know the rules. I can specify the rules for the endorsers. So I might have various endorsement policies depending on whether I trust the endorsers or not. I might require a majority of the endorsers to agree on a certain value. And this is especially noticed because we are having non-deterministic executions. Finally, there's an independent set of orders. Their job is to execute the consensus protocol, and they establish the order on the blocks and hence on the transactions. The orders just order things, yeah? They do not maintain the blockchain ledger or the smart contract or whatever, and they can also, it's pluggable, so you could use, if you assume that the orders might be malicious, you can use PBFT. If you assume that the orders can only crash, then you can use Paxos. Let's look at an example. Here we have 3 different applications, the green, the blue, and the yellow. Each of them has a set of endorsers. You notice that the number of endorsers depends on the application. So the green has 2, while the yellow has 4. And then we have a set of orders, and they do not have a copy of the ledger. The ledger is available at the endorsers, but not at the orders. All the orders are doing is to execute transactions, and that's it. Sorry, is to execute the order, to establish the order in which the blocks should be maintained and the transactions should be executed. The endorsers are the ones who are going to execute the transactions. So if we have various requests coming. You basically, a client sends it to the endorsers execute it and return the result of the execution. Notice the execution is happening first. Now, the various applications might have different endorsement policies. A client receives all the results from the endorsers, and based on the policy decides what to accept or not to accept, and then send them to the orders. Now the orders are going to execute a consensus protocol that establishes the order among the various requests that are coming from the different applications. So an order is established, and that order is sent to the various endorsers. The endorsers validate that the transactions are executed and are resulting in the correct answers according to the execution that had taken place. And once that is validated, they have to establish if all read-write conflicts have been executed in the right order. Once that is done, it is executed and we are done. Of course, we can have a problem if there are lots of conflicting transactions. They access the same record and one of them is a write. So write or write read. These are the standard things. So for example, if we had in this case, the green application was writing record A and the blue and the yellow were both reading record A. Now we have a conflict. So once the order is given, then the endorsers need to establish what are the conflicting transactions, and there is a conflict between the write and the green write and the blue read, and the green write and the yellow read, and so those are aborted. Notice in a way it's because the two reads were executed on the initial state. They do not reflect the state of this write operation. So the write operation was ordered before them, and you have an inconsistent behavior. So as a result, Hyperledger in its basic form shows poor performance when there is a lot of conflict among various the workload has a lot of contention. Now, there have been, Fabric is actually quite popular, and as you see on this slide, there have been lots of innovations and ways in which to improve the performance of Fabric. And you'll notice these are all 2019, 2020, so very recent results. So for example, with Fabric++, you it tries to abort transactions early that can never be reordered, so you avoid write-write conflicts, and reorder transactions after the ordering phase, so that if you have a write read, since the read was reading the initial value, we can switch the order and we end up with a read write, so that improves performance. Alternatively, with Fabric Sharp, it used also early abort of transactions that can never be reordered, and presents a reordering technique that eliminates unnecessary aborts, because you can take advantage of some of the semantics of the read and write conflicts. With Fast Fabric, it uses various different data structures and caching techniques, parallelizes the transaction validation pipeline, and there is an execute order execute Fabric, where basically there is both a pre-order, which is what we saw, and a post-order execution. And the post-order execution is added after the validation phase to re-execute the transactions that were invalidated due to the read-write conflicts. I want to emphasize again that for Hyperledger Fabric, the execution of the execution of the transactions does not have to be deterministic. It can be non-deterministic. What you've noticed I've been kind of alluding to is that if we can capture the order in which the reads and the writes by the different transactions are being issued, we can actually take advantage of this to improve performance. And this is a notion that we are familiar with in databases, which is a serialization or a dependency graph. So a dependency graph basically exposes the ordering dependencies or conflicts between transactions. So for example, we have various transactions here, T1 through T5, and in each case we have the read set row. For example, T1 reads A and writes A and B. Then they are going to be ordered, and the order now will be captured between the different dependencies that arise between the different transactions. So for example, in this case, we have T1 was executed and it wrote A and B, and then T4 read B, and it follows it in the order. Left is, this is the head of the blockchain. So as a result, T1 must be executed before T2. Likewise, T5 writes T3 writes E, that is read by T5, and T2 writes D, that is read by T5, that is written by T5. So in this case we have T5. What does T5 do? T5 reads E and writes D. So as a result, we have T3 that writes the value that was read by T5, and T2 writes the value that was written by T5. So there is an order. T1 must be executed before T4, and T5 must be executed before either T3 or T2. But T2 and T3 can be executed in parallel, and T1 and T5 can be executed in parallel. So again, going back to this model where we have clients, orders, and executors, but in this case we're going to order first. So it's a pessimistic approach. You issue the transactions, you send it to the orderers, it finds an order among these things, but not only it finds an order among the transactions, it creates a dependency graph. And the dependency graph with the order is sent to the executioners, who are going to determine how to execute the transactions. Let me go into a little bit more details. So we have the ordering phase. A client issues a request. This request arrives at one of the orderers. It executes a consensus protocol among the different orders to come up with an order, and it waits for a number of transactions to arrive to create a block, creates an order among these different transactions, as well as a dependency graph. The new block with the dependency graph is then sent to the executioners, and the executioners independently receive the these different blocks with the dependency graphs. Notice we have here two applications. We have the green application on top and the blue application on the bottom. Each of them has an identical set of transactions in some order. They are going to be executed in that order, one by one. And what we do is we can execute now in parallel, because the two different transactions that can be executed in parallel, these two can be executed first together, this one and this one, and then we can, once these two are executed, then we can execute all of these three in parallel together. Once this is done, all the different operations are sent, all the different results are sent, the blocks are sent to all of the transactions, and a new block is added to the blockchain because it has been executed at all the sites. This works as long as all the dependencies were within each transaction, within one application. If you recall in the previous exam, on the previous slide, there was a dependency among the blue transactions and a dependency among the green transactions. But what if there is some dependency between transactions of different applications? Now, the agents of these applications cannot execute transactions independently. So what we need to do is, if there is such a dependency, for example, from 3 to 7, from a green to blue, then we need to send messages as soon as the execution of each transaction is completed. So you send it out to everybody. So if anybody is waiting for some dependency, they become aware of it. of course the number of messages exchanged becomes very big. Alternatively, we can send messages when the execution results are needed by some other transaction. So it's a difference between a pull and a pull. And in the paper, we actually explore the trade-offs between these two different approaches. So in general, we have a pessimistic and an optimistic approach. You either order first and then execute, or execute first and then order and then validate that the execution was done in the right way. With Hyperledger Fabric, it supports non-deterministic executions. It executes first, and then, because it does not submit transactions with inconsistent results. If you have different results, the policies are going, the endorser policies are going to result in excluding those. On the other hand, if we have high contention workloads, an approach that is optimistic suffers from that. And actually, that's very similar to behavior in standard database systems, which are trade-offs between a locking approach and an optimistic approach. On the other hand, if I use a pessimistic approach like Power Blockchain, which is executing the order first and then the execution, but taking advantage of the dependency graph to improve the performance, in this case, we are supporting high contention workloads. The trade-off is that we cannot support non-deterministic executions because it validates the non-determinism at the end and will abort the transactions after all the work has been done. So this dichotomy is very interesting and reminiscent of things we've seen before. So in general, we have three different known architectures. At a high level, it's order, execute, or execute order. When you execute order, you need to verify at the end. If you're doing order execute, then if you generate a dependency graph, you can support the parallel execution of transactions. One big advantage of an optimistic approach is that you can actually support non-deterministic executions. On the other hand, a pessimistic approach, which order first, supports high contention workloads. Okay, we'll take a break now and we'll continue after the break.
Welcome back, folks. In this part of the tutorial, we will explain techniques that have been used to make permission blockchain more scalable. For those of you who do not know me, I'm Divi Agrawal, and I'm on the Faculty of Computer Science at University of California at Santa Barbara. So before we dive into the scalability solutions for permission blockchains, let us briefly review the overall setting for the permission blockchains itself. So as Amr mentioned in the introduction, the application context that we are considering is really typically involves multiple enterprises, such as those involved in a supply chain application. And the need is that all these entities want to maintain a data infrastructure that can be manipulated and maintained by them collectively. So the challenge here is that even though these entities come together to participate in this particular application, for example, the supply chain application, what they do not have is they do not have the necessary mutual trust where they can grant this capability to one single person or one single entity for maintaining the ownership of this data infrastructure. Okay, so this is where the blockchains come into play. The blockchain provides a guarantee that the data in the block is immutable or is tamper-proof, and that gives a peace of mind, or you can say that they have some trust in the data itself, right? So this gives them the comfort level that they can use a shared infrastructure in which these blockchains will not be tampered with, and each of them can maintain a copy of this data in their own private infrastructure. Now, the flip side of this equation is that in order to kind of maintain this infrastructure, which will make sense to all of them, we have to provide mechanisms that will ensure that these copies of this blockchains that are being maintained by multiple entities are mutually consistent with each other. And the way that mutual consistency comes about is by ensuring that the manipulation operations, or equivalently the transactions, are globally ordered in consistent manner across all entities. And that's where we use this notion of a consensus protocol, and in the context of malicious environment in particular, we use what is referred to as the PBFT, and that was introduced earlier. Okay, so with that background, what we do is we come to the issue of scalability of these infrastructure, and the need for scalability arises because, as the number of organizations grow, or even if the number of entities do not grow, what may happen is the number of the transactional needs of each individual entities grows over time, and as a result, what is going to happen is that you want to be able to process larger number of transactions, basically, in the system. And the question is, can permission blockchain be made scalable to process this larger number of transactions in the system? Now, a typical solution for making these infrastructure more scalable is by throwing more resources to the system. And the question is there an inherent limitation in permission blockchains where just adding resources is not going to solve the problem? And that's is what we are going to be looking at during this part of the tutorial. Okay, so with that, so our underlying thesis is that we want to find out if a blockchain system has the ability to process an increasing number of transactions by just adding resources to the system. So before we get into just adding resources, let's see if there are any alternative solutions to this problem. So there are typically two classes of solutions for scalability, and one of them comes about from the area of there is this notion of lightning networks, where basically what they do is they have this notion of building blockchains that reduce the transactional requirement on the main chain, on the blockchain, by offloading the workloads to lower levels. So the idea can be illustrated by using this using this picture. So you can think of that the blockchain itself is really a control plane, okay? And you have these the entries in the blockchain are smart contracts, which essentially open what is referred to as a payment channel, private payment channel for interactions among entities in the cryptocurrency context. So what you do is you basically, at some point, you realize that there are two entities who want to interact with each other, and what you do is in the control plane, or in the blockchain, you lock the state at a certain point and you open what is referred to as a payment channel. And what then happens is, as these entities who wanted to interact with each other, they interact with each other by doing transactions using this payment channel. And once the interactions are completed, what they can do is they can close the channel and the modified state can be incorporated into the main blockchain. So this is the idea of Lightning networks, and what you're doing is basically what's happening is you're able to scale the system by kind of partitioning kind of transactions into two categories: the control transactions, which is the locking the state and finalizing the state, or creating these payment channels, and the payment channels are used for performing the local transactions. So next, I would like to examine how we can potentially increase the number of transactions that can be processed by adding more resources to the system. So this is going to be what is referred to an on-chain solution, and it is basically we are going to make modification to the blockchain itself. Okay, so the one way to add resources is by making individual nodes more powerful. So you basically so this is referred to as the vertical scaling, and you add more power to each node. But as you know that adding more power has its physical limits. Basically, there is a limit as to how fast the machine can be because of the clock speeds, and similarly there is a limit as to how, even if you increase the network throughput, you still have some limitations on the network latencies. So the vertical techniques only can take you so far. And the other problem with the vertical techniques is that what can happen is if some of the machines are not as powerful as the more powerful machines, then what happens is the system can operate at the slowest component in the system. So this is the problem with the vertical technique. As a result, at least in databases, the technique that is more used is what is referred to as a horizontal technique. And conceptually, what you can think of it is basically this is the idea of what is referred to as clustering or partitioning, where you essentially try to overcome the scaling problem by doing a divide and conquer. So instead of trying to solve the bigger and bigger problem, you break the problem into smaller pieces and solve it. So that's the idea of what is referred to as the sharding. And what I'm going to do is I'm going to illustrate these ideas based on some of the recent work that has appeared in the context of blockchain, and where the sharding technique has been used. Okay, but before I give you the individual results, what I'm going to do is I'm going to kind of show you as to where the complexity in the system arises in the context of permission blockchain. Okay, so as you know, I think as I've already mentioned, that one of the key component of the permission blockchain solution is that in order to maintain the mutual consistency of the copies of the blockchain that is maintained at different places, you have to make sure that there is global ordering of transactions at all times. And this global ordering component is performed by the global consensus idea. Okay, so when the scale of the system is relatively small, you basically have few number of orders. So for example, here we have 4 nodes. So this is typically a 3f+1 scenario. So that means we can handle up to 1 malicious failure. And what that does is with 4 machines, you can achieve the ordering relatively fast. Okay. In order to scale the system, what you may want to do is you would like to introduce more machines in the ordering capacity. And what that does is, because of the centralized nature of this consensus mechanism, which requires, which is basically, as has been pointed out, is linear to the number of machines that are involved in the consensus, as well as the n-squared messages that are needed for communication. What that does is, by adding more machines, you're going to slow down this component. Okay, and if you add, if you continue on this round, this is not going to work because it's going to become slower and slower. So the idea of sharding is, what you do is you basically, break your ordering component into multiple independent pieces, and the notion would be is that you basically shard the blockchain into different categories. So here we have like represented by 4 categories, and applications that need to access the blue shard basically have to only do the ordering in the context of the blue orderers, and similarly the greens will go to the green orderers. Okay, so the trade-off is, by partitioning, what you have done is you have made things more scalable, but the sacrifice you have made is that even though you have larger number of machines, the number of failures that you can still tolerate is limited to is limited. So for example, if you had 10 machines, you could handle 3 failures, but if you divide the 10 machines into 3 groups, then you can only handle 1 failure in each group. So that's the trade-off that you have. Okay, and the advantage of this approach is that you can, as long as your interactions or your transactions are within the shard, then they can be done actually concurrently. So you really increase the capacity 4 times in this context. But the challenge that arises is when there are interactions or transactions that have to cross the shard boundary, that are referred to as the cross-shard transactions, then you have to introduce mechanisms so that you make sure that the ordering is consistent across these 2 different shards. Okay, so basically, this is the conceptual problem, and I'm going to now illustrate how the different protocols that have emerged in the last few years and how do they solve these type of challenges. So one of the first one is a VLDB 20 paper, and this is from Mohammad Sadoghi and his group at University of California, Davis. And the setting for this is very similar to what I have described, but they motivate the problem of scaling of permission blockchain in the context of geo-replicated setting. So what they point out is when you're dealing with replicated data, and the context of replicated blockchains that are spread across geographical boundaries, what that happens is, because the latencies increase as you increase the distance between these copies, and that can give rise to inefficiencies in the system. So what they propose is this idea of what they call a geo PBFT, which basically uses the network topology, and they create these localized clusters which are restricted to a geographical domain which is kind of close to each other, and they execute transactions in the context of these local clusters. So you can think of this is a cluster that you're maintaining in California, and there is this cluster that is being maintained, let's say, in the northeastern part of the United States. Okay, so the malicious, so they run PBFT in a much smaller context, and what they have instead of trying to run a global consensus algorithm, what they claim is that once you have run a PBFT and you have a certified commit achieved at the local level, then what they can do is they can actually, instead of using a Byzantine consensus algorithm across geographic site, they can use something what is referred to as a global sharing, and they theoretically established that all they need is that they need to send kind of F+1 messages during the global sharing phase, and after that the transactions that have been executed in this cluster and transactions that have been executed in this cluster, they are deterministically ordered by all these nodes, and then then you go and execute these two transactions. So to summarize, the blockchain is completely kind of replicated at all places. They are not sharding the blockchain. So every machine maintains a complete copy of the blockchain, and what they're doing is they're doing a local kind of consensus on a transaction here, and then global ordering of the locally agreed upon transactions. And once the global ordering has been determined, then these things are executed at each machine to ensure that the mutual consistency of the blockchain is maintained at all copies. Okay. So even though kind of the Sadoghi approach or resilient DB approach was partitioning the nodes into different clusters, what it was doing was it was not partitioning the blockchain itself. So the next two, next two protocols that I'm going to introduce, they are going to basically rely on sharding of the blockchain itself. Okay, and once you do the sharding, that has been very effective in the context of database technology. The challenge really comes down to is that when you have interactions that cross the shard boundary, referred to as the cross-shard transactions, they need to be synchronized using some mechanisms. Okay, so there has to be some sort of a coordination. In the context of distributed databases, this coordination happens using two-phase commit protocol, for example. Okay, the first protocol we are going to review in the context of the sharded approaches is what is referred to as AHL. And this is a protocol from, this appeared in SIGMOD 2019, and it is from Bengchen Hui from National University of Singapore and his research group. So the idea, as I said, is it uses a sharding technique in malicious or untrusted environment. I think that is given for us is that we are dealing with untrusted infrastructure. Now, in order to understand, what the solution strategy that this particular protocol uses, what we should do is we should look at the design objectives that the authors have laid out. So one of the first things they want is that they want to build a permission blockchain system for network sizes that mirrors the sizes that are being used in the context of cryptocurrency, for example, the Bitcoin and Ethereum, right? The next goal they have is in contrast to the cryptocurrency, which have very low transaction throughput. What they want to be able to achieve in this environment is they want to achieve a high transaction throughput that is comparable to commercial DBMS technology. So typically this is of the order of 2,000 to 4,000 transactions per second. And finally, they don't want to have a specialized application like a cryptocurrency application where transactions are very, very restricted format. They want to be able to support diverse applications in the context of, in the industries like finance, supply chain management, and healthcare. Okay, so once you laid out the design objectives, immediately the challenges arise. What are the challenges they have to overcome? And this is what the authors kind of outline. So one is, of course, as we have seen, is the one of the biggest challenge or the bottleneck in the context of permission blockchain system is the issue of the consensus protocol, which is based on Byzantine fault tolerance. Okay, so the first thing that they have to deal with is how do you scale the BFT consensus protocol. The second thing, which is right now is going to appear a little mysterious, but they also talk about this kind of the shard configuration or assignment. How do you take your nodes and how do you do the mapping of the shards to the nodes? Okay, so the challenge there, what they say is that you don't want to run into a situation that a particular shard gets mapped into a node where most of the nodes are malicious. So that's, I think, is another challenge that they have to kind of overcome, and they outline a strategy for that. And finally, because they are dealing with multiple shards, they want to be able to enable kind of distributed transaction synchronization. And the observation there is that you cannot use a single coordinator based strategy, because what happens if that coordinator is malicious? So you have to enable or support distributed transaction in spite of malicious transactions. Okay, so having seen the kind of the design objectives as well as the challenges associated with achieving those design objectives, let's look at the solution outline of AHL, which is referred to as, which is a short form for attested hyperledger. So the first thing is, as we mentioned, one of the first challenges is that how do you scale BFT? So what the authors propose is that they are going to use for each node, they're going to make it into a trusted execution environment using hardware technologies such as Intel SGX, and this is going to be available at every node. And with that trusted execution environment, the authors actually demonstrate that they can run BFT, and instead of needing 3 F+1 F replicas, they only need 2 F+1 replicas, even though they're dealing with malicious failures. So that's, I think, is the first step for scaling BFT. Well, that just, by reducing allowing less number of failures, or making the network size smaller with respect to the number of failures, does not solve the problem of the n-squared message cost that is associated with BFT. So the solution they propose is that what we are going to do is we are going to partition the network and the blockchain states into smaller shards. So that way the n-squared cost will be kind of confined to at the shard level. And one observation they make is that when you do this shard assignment to the nodes, what can happen is you can run into a situation where a particular shard is assigned to a nodes where the failure, kind of the number of failures, malicious failure, exceeds the threshold. So that for that they propose a probabilistic assignment, which is going to allow them with a very high degree of confidence that such is not going to be the case. Once you do that assignment, basically what you end up with is a setup which looks very similar to what you have in a distributed database setting. So you have these sharded groups or sharded data, and the sharded data is replicated on multiple nodes, and you're going to run BFT consensus because you're dealing with malicious environment within each shard. Okay, so as long as transactions are confined to the shards, then you can execute them locally. Right? Now the issue of transaction management comes into play when you start having cross-shard transactions. So for that, they basically use a coordinator-based approach, which is used in distributed databases in the classical two-phase commit and two-phase locking protocol, except for the difference that they cannot rely on having a single coordinator or centralized coordinator. So the centralized coordinator can be a problem for two reasons. One, it could be a performance bottleneck, and then two, what will happen if that centralized coordinator happens to be a malicious entity. Okay, so what they do is effectively what ends up happening is you basically have this notion of coordination, but the coordination is achieved not by a single node, but by a group of nodes that is referred to as a reference committee. Okay, and kind of the regular shards are referred to as a committee, and the rest of the protocol flows exactly the same way as two-phase commit protocol is, that when the transaction commitment is initiated, the reference committee basically goes through and proposes a begin transaction and sends out a prepare messages to these committees, and then once the answer comes back, the reference committee basically goes through a consensus round within itself to agree upon the outcome of the first phase of the transaction, and then it goes to the second round, and then finally comes to the commitment or abortion of the transaction. So that's the outline of the proposal. Okay, so one of the problem with AHL is that it has this notion of coordination that has to happen for all global transactions. So the next result I'm going to present is from a paper in SIGMOD 21, and this is based on Muhammad Amiri's PhD thesis work, and it's going to be concurrently presented, but I'm going to give you just a high-level overview so that it can be positioned with respect to what we have seen in the context of other protocols. So the goal is similar, that you want to scale the system, and the scaling is going to be dependent upon sharding. You shard the blockchain into multiple pieces, and similarly you partition the network into smaller groups. Okay, the partitioning of the network, you want to do it in the smaller groups is because you want to limit the amount of kind of overhead, or limit the overhead associated with the consensus that has to be achieved among all the network nodes. Okay, so the goal, kind of the main goal of this paper would be is that we want to eliminate the need of coordinators. So you want to basically sort of still support cross-shard transactions, but the cross-shard transaction execution has to be based on sort of the kind of decentralized approach rather than a centralized two-phase commit or centralized coordinator-based approach. Okay, so the observation in our case, in this case, in the case of Sharper, is that we have a predetermined idea that there is this value f, the number of failures, malicious failures in the system. Okay? And typically the assumption is that the number of failures is much, much smaller than the number of available nodes in the system. So if you have that sort of upper bound on the number of failures, what you can do is you can use that information, and based on that you can create these node clusters, which is going to satisfy that every cluster has at least 3f plus 1 if you are dealing with malicious failure, and once you have that, then you know that you will overcome the issue of failures. Okay, so you partition the network into these network clusters, and then you basically also do the same thing with respect to your data. So the data is sharded into these mapped into these clusters. Okay, and now the question is, how is the blockchain ledger maintained? And I'm going to illustrate that in the next. So let's look at what happens, kind of the global view of the blockchain. So this is the starting point, and what you have is basically you are going to, instead of having a linear chain, now you'll have parallel chains in some sense going for each of the shards of the blockchain. Okay, so you have the blue chain, the green chain, the yellow chain, and the red chain. Okay, so if your transactional activity is confined to each shard, then essentially what you have done is you have taken your original kind of the single chain, and you have basically broken it up into 4 different parallel pieces, right? That's what you have done. But in reality, what happens is you cannot be sure that the transactional activity is going to be confined within a single shard. So in order to do that, you want to be able to support cross-shard transaction, and that's what you are seeing. It's being illustrated here in this picture, is that you have these gray nodes are the cross-shard transactions, and basically the arrows correspond to these cross-shard transactions are interacting with multiple shards. So for example, this particular transaction T12, T22 is dealing with both blue and the green shard, and similarly this transaction is dealing with these strands. So as a result, the blockchain, the view of the blockchain becomes a directed acyclic graph, where the transactions are not maintained in a total order, but transactions are maintained in a partial order. Okay, and the ordering is determined by the cross-shard activity that is happening here. So for example, here is a transaction which involves all 4 transactions, all 4 shards, and therefore it is ordered with respect to all the activities in the 4 shards. Okay. Now the question is, what does each of the shard maintain? What is the view of each shard? So the global view that is illustrated here is not maintained by any particular site. Instead, each shard maintains its view or its projection of the global view. So for example, on the blue shard, you have these transactions, the blue transactions, in addition, the gray transactions that have been included. So from that sense, if you see, this is basically a permission blockchain in the blue shard area, augmented with these cross shard activity. Okay. So what does, how do we achieve consensus? How do we ensure kind of ordering of these transactions that can be thought of as local and non-local transaction? So what you need is 2 types of consensus mechanism. One is what is referred to as an intra-shard consensus, which is essentially used to order the transactions that are confined within a shard. And this can be, depending upon your failure kind of situation, you can either use if you are confined to the crash-only failures, then you can use a Paxos-like protocol. But if you're dealing with Byzantine failures, then you can use PBFT. So I'm going to assume that we are dealing with PBFT. Okay. The other thing that now is needed is we are going to allow cross-shard transactions to be executed. Okay, when cross-shard transactions are executed, then you have to make sure that these cross-shard transactions are kind of synchronized with respect to the local executions that are happening in the in the multiple shards that are going on. Okay, so and here again, if we are in the crash-only environment, then you can use a Paxos-like protocol. But if you are using, if you are in a malicious environment, then you will use a PBFT protocol. So I'm going to now illustrate. So I think the intra-shard consensus is really a pluggable protocol that is, you use essentially whatever we have already been using in the past in the context of a permission blockchain. The new thing that we have to devise is these cross-shard consensus protocol. And I'm going to give you a very high-level idea as to how cross-shard consensus is achieved. And so basically, when a client initiates a request for a cross-shard transaction, it goes to kind of one of the leaders of the shard, and that leader of the shard sort of takes over that request and sends the the message, the proposed message to all the sites in both the shards. Okay, and then you have to wait for the necessary f+1 messages from, so the coordinator or the leader of this who's coordinating the execution of this transaction has to wait for f+1 messages, not only just one set of f+1 messages, but it has to receive f+1 messages from each shard individually. So there have to be f+1 messages coming from here, and similarly f+1 messages coming from here. And from as far as the sequence numbering goes, the sequence numbering is initially decided for this shard P1 is decided by the leader here, but for shard P2, each of these are going to send the corresponding number. Okay, and once the execution, once you have received the necessary number of messages, then you can accept the execution and order the transaction accordingly. Okay, so that's what's going to happen is you basically decide on the commitment of the transaction and send out the messages to the necessary number of nodes. Okay, with respect to the Byzantine nodes, it's very similar, where you send out the request to the leader of one of the shards, and the leader of one of the shards coordinates the execution of this transaction on multiple shards by sending out the necessary number of proposed messages, and then you have to wait for accept messages. And here I think the accept messages have to be sent to all the sites. 2 f+1 messages have to be sent, and you wait for 2 f+1 messages from every shard, because you're dealing with, you have to make sure that you don't have any Byzantine behavior. Okay, so that's the difference between the crash only and the Byzantine nodes, that you have to wait for 2 f+1 matching accept messages, and then you have to send out that many messages for the commitment of the transaction. Okay, and once you have achieved that, then basically the transaction is committed. Okay, so the advantage of this protocol is that, one of the things you might notice is that if there is, you basically, one thing you notice that in the context of this particular protocol, the cross-shard transactions are only synchronized with respect to the shards on which they are executing. So if there is another transaction that is executing on a set of disjoint shards, the execution can be done concurrently. So that I think is good, because that you don't have a global bottleneck, meaning that distributed transactions don't have to be synchronized in a centralized manner. Okay, so that's the good side, right? But there is obviously, the good side comes with the bad side, and the bad side is I'm going to just outline the problem and not go into the deep details. I think I'm going to refer you that the solutions are going to be found in the paper. But the problem is that you could run into, situation where you have, two concurrent execution of 2 cross-shard transactions, and they both involve they have an intersection of their execution on a particular shard. And what happens is, because we are in an asynchronous environment, what can happen is the order in which the messages arrive from these 2 transactions, for these 2 transactions on this cluster, could be different at different nodes. Okay, so because of that, you could have a problem in the following sense, that this particular node might order these 2 transactions as number 10 and 11, whereas this one might order it in the reverse order. Okay, so the protocol has to make sure that such kind of discrepancies are taken care of, or has to be resolved, and what the way it is handled, it is that whenever there is this conflict that occurs, then it is handled at the leader of that particular shard. So the leader associated with shard P2 is going to make a go through and will make a super proposed message, and it is going to resolve these type of conflicts. Okay. Now, in the same vein that what I've described, when you have the situation, what you can also have is that because of this reordering of these messages, you could have a problem of a deadlock. And I'm going to refer to the paper that, so you have to time out and you have to re-execute the protocol and so on. Okay, so one of the things that can be done so one of the solutions that is proposed in Sharper is that if you are in a high contention environment, what's going to happen is you are going to routinely get into this conflicting situation that I described in the previous slide. So what they propose is, at the expense, if you know that you are in the high contention environment, okay, where these type of overlaps of this type of conflicts are going to arise frequently. So instead of executing them just using the two-phased approach, what it does is it introduces a kind of an extra phase, which is referred to as a super propose, where the leaders of all the shards basically go through a coordination process, and using that coordination process, they come up with some understanding as to how these transactions have to be ordered, and then proceed with the regular flow of the transaction execution. So this is, there is a trade-off. You introduce more latency, but then you reduce the amount of conflicts and corrections that have to happen in the system. Okay, so this, I think, should give you an idea of what is happening and how sharding and partitioning of the network is being used. So let me summarize our discussion on scalability. We saw various approaches for making permissioned blockchain systems scalable. And the first approach, what it did was it basically partitioned the network into smaller clusters, but maintained a centralized or a single ledger across all the sites. And with that, what we were able to do was the consensus was carried out in a localized context, and then you could do the replication of the ledgers or transactions across the global, all the global cluster using a replication technique. Clearly, maintaining a single ledger is not, that does have its own limitation, and that was exploited in the technique that I presented as the AHL technique. And here, what you did was not only you partition the network, you also partition or sharded the ledger itself into different clusters. So there was a mapping of the shards to the cluster that was maintained. And in this context, if your transactions are confined within a cluster, then you could, you don't need you can scale the system. However, what we found was whenever you have a cross-shard interactions and you're bound to have that kind of interaction, then you need to do some sort of a coordination across different clusters. And the AHL approach in this context uses a coordinator-based approach, which is very similar to what we know as two-phase commit in distributed databases, with a main distinction that instead of having a single node serving as a coordinator, they actually have to use a notion of a reference committee that would serve as a coordinator. And the reason you need to use a reference committee is because we are dealing with malicious environment. So one of the problem with, one of the drawbacks with the AHL is that what can happen is as soon as you have any amount of cross-shard activity, you have to have this centralized coordination that has to happen through the reference committee. Sharper, as we saw, what it does is it basically kind of eliminates the centralized coordination, and it only requires coordination among the clusters on which the transaction was involved. So that, I think, reduces the synchronization requirement significantly, because you could now allow multiple cross-shard transactions to be processed in parallel in the system. So this, this basically, this is generally these are the flavors of the algorithms. One of the problems with the flattened approach is if the clusters are far apart, then you are going to achieving cross-shard consensus is going to incur in high latency. So with that, I am going to close this part of the tutorial, and we'll open to question and answers session. And hopefully, if there are things that were not clear from the recorded portion of this talk, then we can take it in Q&A, and we will try to answer those questions. Thank you.
Welcome to the next part of the tutorial. In this part, we want to talk about blockchain confidentiality. To motivate blockchain confidentiality, we consider supply chain management as an application. In supply chain management, we have different enterprises, different participants like middleman, supplier, carrier, manufacturer, bulk buyer. These participants, they want to work with each other, but they don't trust each other. And as a result, they don't want to share their data with each other. So we need confidentiality here. We need confidentiality of data. And we have some global communication, some global transactions between these enterprises, where these communication follow service level agreement, which is agreed upon by all participants. For example, the bulk buyer places order manufacturer places order with middleman. We have arranged shipment, we have delivery, we have pick order, and we have all types of these global communication or global transactions among these enterprises. However, each of these enterprises, each of these participants has its own local transactions as well. And the blockchain system needs to support both public or global as well as private or local transactions. So one solution is to say, okay, we replicate a single blockchain on every party, and then this blockchain maintains all private as well as public transactions, and it is replicated on every participant. However, it doesn't preserve the confidentiality of data, because every party has access to all transactions of all participants. As I said, we need to maintain all public and private transactions. And if we replicate all private transactions on every party, then we cannot preserve confidentiality. And also, it has poor performance, because for replicating every transaction, we need to run some type of consensus protocol. And for for example, the manufacturer need to maintain private transactions which are for example, supplier, and it results in poor performance because first of all, it needs to maintain transactions that are irrelevant to manufacturer, and second, it needs to be involved in consensus protocols for those transactions. Another solution is to say that, okay, we can maintain like two blockchain ledgers on each party. A public blockchain ledger, which is basically this green ledger, which is replicated on every party and maintains these public transactions, and each party maintains its own blockchain ledger or even its own database. But the problem is data integrity, because these transactions are related to each other. For example, the local transaction or the private transactions of manufacturer are based on this public transaction. Based on this place order, the manufacturer decides how to basically manufacture some product. So this is these two blockchains are like dependent to each other, and we have data integrity issue. So Caper is an example of a blockchain that tries to solve confidentiality. In Caper, the blockchain ledger is a DAG structured blockchain ledger, and the logical view of the blockchain ledger is as follows. We assume that we have 4 enterprises in different colors. So there are 3 different rules. First of all, there is a total order between transactions that are initiated by the same enterprise. So let's say the green enterprise initiated T11, T12-1, T13, T14, and T15. Or the blue one initiated this blue transaction as well as this one. So we have a total order among transactions that are initiated by the same enterprise. Second, we have a total order between global or public transactions. So this is a public transaction, T12-1, T23-2, and T34-3. As can be seen, these public transactions, the sequence number has 2 parts. One part shows the order among the transactions of the initiator enterprise. So this 12 shows the order among the transactions of basically the initiator enterprise, T11, T12, T13, T14, T15. And the second part shows the order among the public transactions or global transactions. So we have T1, T2, and T3. So there is a total order between them. And as can be seen, local transactions might use data that is coming from the global or public transactions. So T13 use data that is coming from here. So these arrows shows that T14 uses data that is coming from here. T15 uses data that is, or T42 is. And this left-hand side figure is the logical view. This is not maintained by any enterprise. Each enterprise maintains its own view of the logical view. So enterprise one maintains its own view that includes its local or its private transaction as well as all global transactions. Enterprise 2 maintains its local transaction as well as all these 3 global transactions. Similarly, Enterprise 3 and Enterprise 4. So each enterprise still maintains a DAG structure, basically ledger. So we need to run local and global consensus. Local consensus for those basically local transactions, which depends on the failure model of nodes. Crash-only failure, we can use Paxos. Byzantine failure, we can use TBFD. Global consensus needs for those three like global transactions, white boxes. In Caper, there are three global consensus. One is using a separate set of orderers, one is a hierarchical global consensus, and one is a one-level or flattened global consensus. Using a separate set of orderers, let's assume that we have like 4 different enterprises, alpha 1, alpha 2, alpha 3, alpha 4. Each of these lines is a node. So alpha 1 has 3 nodes, alpha 2 has like 4 nodes, and so on. And we have a separate set of orderers, O1, O2, O3. This is kind of similar to what has been used in Hyperledger Fabric. So in Hyperledger Fabric, we have a separate set of orderers, right? So it is kind of similar. So we have a disjoint set of orderers, and they try to globally order cross-enterprise transactions. So when a request comes to the enterprise alpha 1, they first run their local consensus to ensure that nodes in alpha 1 in the enterprise alpha 1 agree with the order, and then they send the order request to the orderers. Then they run global consensus, and then they send a sync message to everyone, including this sequence number. These are basically those two sequence number in the ledger that I showed you, that T2 T1, that one was the global sequence number, one was the local sequence number. So they send this sync message to everyone and saying that, okay, this is a global transaction, so please append this to your blockchain ledger. So the orders approach comes with an extra cost of adding orders to the system. In the hierarchical global consensus, since enterprises do not trust each other, we run the Byzantine fault-tolerant protocol among these enterprises. And at each step of the Byzantine fault-tolerant protocol, we run the local protocol of each enterprise within the enterprise. So you see that in the first step, we have the proposed phase, and then they run Paxos within the enterprise alpha 1, we run PBFT within the enterprise alpha 2, and so on. And then we have the second phase, which is an N-square phase, and then Paxos, PBFT, and so on, and then commit phase. So in that way, we distinguish the trust at the node level and at the application level. So here, the application decides, all nodes together decides to vote for that particular message or not. And the third one is a one-level global consensus. So the hierarchical consensus requires an expensive two-level consensus protocol, because in each step of the global consensus, we need a local consensus within each enterprise. In one level, basically, we have a three-phase protocol where all nodes are going to talk to each other. And at each step, if we receive messages from 2/3 of enterprises, not all of enterprises. If we receive the message from 2/3 of enterprises, it's sufficient. And from each enterprise, we need to receive message from local majority of that enterprise. So what is local majority? If the enterprise has 4 nodes, or let's say 3f plus 1 nodes, then we need message from 2f plus 1 nodes of them. If it has 2f plus 1 nodes, we need messages from f plus 1 of them. So we need message from local majority of 2/3 of basically enterprises, or let's say more than 2/3 of enterprises in the one level global. But note that here we have communication among all nodes. So we assume that enterprises know the nodes of other enterprises, whereas in the previous one, we assume that enterprises do not know what are the nodes of each other. So they just know that there is an enterprise, and we don't know what's happening within that enterprise. So this is like a trade-off. So another way to basically guarantee confidentiality is using Fabric and using different channels. So this is another view-based way to guarantee confidentiality. So in Fabric, we can use different channels. So saying that we have like 8 different like enterprises, or let's say different nodes, or we can interpret these nodes as different enterprises or different like single nodes within the same enterprise. And we want to preserve confidentiality. We don't want these 4 nodes to be aware of the data of these 4 nodes. So we can use channels. We can separate these 8 nodes into 2 different channels. So a channel is basically a private subset of communication between a set of specific nodes. So these nodes maintain the same data. These nodes maintain the same data. And they might still share the same set of orders, or might have different set of orders. And this channel has its own ledger. This channel has also its own ledger. And these orderers know that, okay, if transactions are coming from this channel, they have put them in their own block, and from this put them into like the green block and the like red block. But here the problem is, if we have a cross-channel transaction, then the processing is challenging. And another way again to address confidentiality is using cryptographic techniques. So we can still have like the same blockchain ledger, maintain the same blockchain ledger on every node, but we can use like cryptographic techniques and basically encrypt some transaction, some private transaction. So this idea is used in Fabric and in private data collection. So within a single channel, we can have private and public data. So these 2 nodes can have private data, so have private like data collection. These nodes have also private data collection. So as can be seen, the ledger, they maintain the same ledgers. They still maintain the same ledger, but the ledger, we have like transaction that is like purple transaction. We have green transaction. This green transaction is hashed, so it can be seen only by N1 and N2. This pink or purple transaction is hashed, so it can be seen only by N3 and N4. So, so there is still a single shared ledger between all nodes, but the ledger might include transactions that are hashed. The problem here is the cryptographic cost and basically the low performance, because all nodes need to maintain the ledger, the same ledger, and the ledger might include many private transactions that are irrelevant to the node. So this green node maintains like a transaction, this like T1, that is irrelevant to the node. So in this part, we talked about view-based techniques and cryptographic techniques. So in view-based techniques, the problem is managing these views and establishing consensus among all views. So whereas in cryptographic techniques, the cost of managing views is lower. However, in cryptographic techniques, we have overhead of maintaining transactions on irrelevant enterprises. Welcome to the last part of the tutorial. In this part, we were going to talk about verifiability. Verifiability means checking some predefined global constraints on the entire system in a privacy-preserving manner. So earlier on, we talked about confidentiality. In the confidentiality, we said we have a set of enterprises, a set of participants. They want to collaborate with each other, but they don't trust each other. And the goal was to ensure that the blockchain system guarantees that these enterprises do not see the data of each other. Basically, the blockchain system guarantees the confidentiality of enterprise data. But here, in verifiability, we want to go one step further. We want to ensure confidentiality, and then we want to enable different enterprises to verify some property on the data of other enterprises in a privacy preserving manner. So we want to enable, for example, enterprise A to access the data of enterprise B in a privacy preserving manner to verify some property, to verify some constraints, where here we mainly target some global constraints which are known by all these enterprises. So to motivate verifiability in this part of the talk, we mainly target one application, which is a crowdworking application. So we are going to talk about crowdworking application and basically the challenges that crowdworking environments face, and then how blockchain systems, permissioned blockchain systems, can help us to resolve these challenges. Crowdworking platforms have grown in number, diversity, and adoption. So, and they are envisioned as key technological components of the future of work. In a crowdworking scenarios, the requester sends a request to the platform like Uber and Lyft, and the platform forwards the request to some of the workers. A worker might send a contribution to the platform, and the platform forwards the contribution to the requester. The requester sends the reward to the platform, and the platform sends the share of the worker to the worker. So as can be seen, the crowdworking platform is an online intermediary between requester and workers. These crowdworking environments, however, need to address several challenges. First, we need to guarantee the compliance of crowdworking platforms. For example, the Fair Labor Standards Act, or FLSA, says that the total work hours of a worker per week may not exceed 40 hours. So a platform, a crowdworking platform, needs to guarantee this regulation for all its workers. So if we have hundreds of workers, or in case of Uber or Lyft, if we have thousands of workers on a platform, we need to ensure that no worker works more than 40 hours per week. Another example is Assembly Bill 5 or AB 5 that entitles workers to greater labor protections, such as minimum wage laws or sick leaves or something like that, and which is recently overturned by CA Proposition 22 that imposes its own set of regulations. So we have these global regulations, and these platforms, these crowdworking platforms, need to guarantee all these regulations. And there are many of these type of regulations. The second challenge is the crowdworking environments are not that simple. In real world, we have like more than one platforms, like we have Uber, we have Lyft, we have Curb, we have Lyft. And requesters usually send their requests to more than one of these platforms. So like most of us as requesters have like both Uber and Lyft on our cell phones. And on the other hand, workers also often work on several platforms. So a driver works for both Uber and Lyft. So it makes the situation very complicated. And finally, we want to preserve the privacy rights of participants. Basically, we want to ensure that no participant obtains or infers any information beyond what is strictly needed. So for example, if a driver works for both Uber and Lyft, the driver doesn't want either of them know that she works for the other. Now it makes the problem very difficult. Why? Because on one hand, we want to enforce regulations. And to enforce regulations, we need to have some degree of transparency. For example, if we want to enforce that a worker works at most 40 hours a week, we need to know that, okay, this worker works like this week, this worker works 30 hours for Uber and 10 hours for Lyft. So as a result, the total is 40 hours. So this worker is fine. But on the other hand, we want to preserve privacy. The worker doesn't want others to know that, doesn't want the Lyft to know that the worker works for Uber or vice versa. So we want to basically we need to reconcile transparency with privacy, and this makes the problem more complicated. So if we want to summarize the problems that we have in such contexts, first, we want to guarantee the compliance of crowd-working platforms with regulations. Actually, in the currently there are some local or per platform regulation exist. For example, both Uber and Lyft have such local regulations. They don't allow a driver to work more than 12 hours a day. But a driver who works for both Uber and Lyft can drive 12 hours for Uber, switch the platform, and work 12 hours for Lyft the same day. So you see, these regulations are currently per platform, are local. There is no like such global regulations. The second problem is we want to have a transparent and privacy preserving regulation enforcement. We want to enforce these regulations such that the privacy of participants is preserved. And finally, we want to have collaboration among these independent and competing platforms. And why do we need such collaboration? For two reasons. First, to enforce global regulations, because as I said, if I have a regulation that says, like FLSA rule, that says a worker, a driver can work 40 hours a week, and the worker works for both Uber and Lyft, then the worker might want to work for Uber like 20 hours, for Lyft 20 hours, or work for Uber 10 hours, for Lyft 30 hours. And this is not determined beforehand. During the week, we can say. So whenever a task is coming and we want to assign this task to that worker, we want to ensure that are we allowed to assign this task to this worker? So we need some collaboration between these platforms to ensure that we are allowed to assign this task to this worker. And this should be in a privacy preserving manner. So this is one reason for collaboration. And the second reason for collaboration is we might have complex tasks that may need multiple collaborations. So an example of these tasks are like microtask platforms. So consider like an NLP task, a summarization task. A requester comes with a summarization task. A requester has a text, a long text, and wants like different, like maybe 10 different or 100 different workers to summarize this long text. So the requester might submit this text to like Amazon Mechanical Turk, Prolific, and I don't know, maybe Microworker, 3 different microtask platforms. From the requester point of view, it doesn't matter which worker from which platform sends basically a contribution for this task. What is important is this requester needs 100 different contribution or 100 different summary for this task. So unlike ride sharing, Uber and Lyft, where each task needs a single contribution, we might, in some like crowd working scenarios, we might have tasks that needs multiple basically answers, multiple contributions. So in such a scenario, these three crowd working platforms, these 3 microtask platforms, Amazon Turk, Prolific, and Microworker, need to talk to each other, need to collaborate with each other basically to say, okay, Amazon Turk say, okay, I have a worker that wants to basically send a contribution. Then Prolific says, I have another worker. So we need to say, okay, this is the first worker, this is the second order worker, this is the third worker, until we reach the 100 workers. So we need 100 different contribution, and we need to have some ordering between these 100 contribution. And why we need that? Because we don't want to accept like the next one, the 101 contribution. So there is a need for collaboration among these platforms, and there is a need for ordering contributions to say that, okay, this is the requested number of contributions, and this is the ordering between them, and we don't accept more than this. And so for that, we need some type of consensus among these like platforms. So it is, again, this is another complexity of the problem. So Separ is an example of system that tries to address this this issue. So in Separ, which is a paper at this year, the goal is to enforce regulations on multi-platform crowdworking environments while preserving privacy. So Separ tries to introduce three main design dimensions. One is the type of regulations that it can support. One is the privacy guarantees that it gives to the participants. And one is the architecture of the system, that it could be fully centralized or partially centralized. So I am going to explain this and saying that, okay, how this is going to connect it to the blockchain system, and how does blockchain help us to basically realize these three goals. So in terms of regulation type, which is the first design space, so we can express regulation as SQL constraints over a virtual universal table. So we can say that, okay, a regulation is basically on like a worker, a platform, a requester. It has some like time cost. It takes like 3 hours. It needs a contribution that like the content of the contribution and so on. And each regulation has like some communication part, which is communication between participants, and it has also some basically content, the content of contribution, the content of the basically request that is needed for that regulation, and so on. And these regulations can be categorized according to their SQL expression. So if a regulation has no join operation, it is simple, and if it needs some join operation, it is complex. Similarly, we can have row only, aggregate only, and mix based on using of group by and having, or basically using aggregate functions. We have another basically way of categorizing regulations. So we say regulations are either enforceable or verifiable. A regulation is enforceable if it must always hold. So for example, a regulation that says a worker must work at most 40 hours a week, it is a regulation that is enforceable. It must always hold, the FLSA regulation, and it is like a maximum work hours. But a regulation is verifiable if it must hold periodically. So if a regulation says a worker must work at least 10 hours a day, 10 hours a week, then you can check this regulation at the end of the week. So you cannot like come to the worker at the beginning of the week and say, okay, you should work 10 hours a week. So show me that, verify to me that you have worked 10 hours this week, because it is the beginning of the week. You need to wait till the end of the week, and then you can check whether this worker has worked 10 hours or not. So these type of regulations are verifiable. You can check this type of this type of regulation periodically at the end of each week or at the end of each month. So, and these are basically minimum work hours if this like type of maximum and minimum are basically enforceable and verifiable. So the second design space is privacy guarantees, that the system basically provides us. So we have a threat model which is system dependent, and for example, a system could be honest but curious, or covert, or malicious. And we have a privacy model. So privacy model, in the vision that we have, the privacy model, we assume that it is pluggable, and we consider three disclosures. So participants in a system are either not involved in a task and have not received a task. Consider the Uber example. A driver might not be involved in a task and might not and also not receive the task. So we have some privacy. Basically, we have some disclosure to such participants. The second type is the participants or the workers and platforms that receive the task but are not involved in task. Like a driver who receives some task, who sees that, okay, there is a traveler that needs to go somewhere, but the driver doesn't accept that task. So the driver learns something from, knows that, there is a task here, there is a traveler that wants to go from some place to another place. So it learns something. So we have disclosures to the platform and workers that have received the task, but that are not involved. And the third disclosures are to the participants that are directly involved in the task. And definitely they have received the task. So the driver who accepts the task. So this is the privacy guarantees. So basically, based on these three disclosures, we define the privacy model. And the part that is mostly related to basically blockchain part is the architectural choice. So when we talk about regulation system, we need to have basically talk about two main critical components. One is the regulation management, where we need to model and enforce the regulations. So we have these regulations. So we need to model them, we need to define them, and we need to model them in a way that is enforceable. And then we need some way of enforcing these regulations. And then the second component is global state management. So the global state of the system, since we said that these are global constraints, and these constraints need to be verified by the entire system, and the system has a global state, so this state needs to be stored. So the global state management is basically the task of storing and maintaining the global state of the system. So each of these two components, the regulation management and the global state management, can be implemented either as a centralized or a decentralized, basically in a centralized or in a decentralized manner. So if we implement in a centralized manner, then it is easier to rapid prototype. However, it is difficult to ensure fault tolerance. It is difficult to ensure guarantee privacy and trustworthiness. And if we implement them in a decentralized manner, then it is indeed more compatible with the multi-platform nature of the system that we have. But on the other hand, it results in more overhead and complex communication protocols among these participants. So with this vision, with these three design space that we had, now we want to define separ. Separ is basically like a point in this design space. So in separ, the focus is on the basically interaction and not the content. So if you remember the U table that we had earlier on, we had worker, platform, requesters, and time cost, and also contribution and so on. So in separ, the focus is on interaction between these worker, platform, requesters. So we don't care about the content of contribution. We don't care about the content of a request. So it doesn't mean that the content of a contribution is not important or the content of a request is not important. Separ is like, as I said, it's like a point in this design space, and it is like an early version of this vision. So yeah, for separ, we just focus on these like interactions. So in terms of regulation, separ supports simple mixed with aggregate basically regulations, and both enforceable and verifiable regulations can be supported by separ. So separ defines basically the privacy model. The threat model is covered non-coding adversaries. So covered means basically adversaries aim to infer anything that can be inferred from the execution sequence, and the adversary is able to deviate from the protocol if no other participant detects it. And by non-coding, there are some scenarios that if basically the participants can code with each other, and separ cannot support that. So that's why separ is basically covered non-coding. But indeed, most coding scenarios can be supported by separ as well. And then we have a basically privacy model based on those three disclosures. And finally, the architecture of separ is a hybrid architecture. So here is where we talk about blockchain. So we have a registration authority. So the registration authority is implemented as a centralized basically component. This registration authority registers participants and models the regulations and distributes some crypto materials to nodes. And we have a multi-platform infrastructure, which is a basically decentralized component, and it maintains the global state within a blockchain. And it needs some basically different type of consensus protocols for nodes within the same platform, nodes across platforms, and basically global consensus for all platforms. So let's see how we guarantee verifiability. So in separ, basically inspired by eCash systems, we implement enforceable and verifiable regulations by managing 2 budgets per participants. And these budgets are basically lightweight, single-use, and anonymous tokens. So let's assume we have a regulation that says each worker can work at most 40 hours a week. We have a registration authority, that every week generates 40 tokens. And what are these tokens? These are lightweight, single-use, anonymous. So it generates 40 tokens for each worker, and basically distribute these tokens to all workers. So every week, each worker receives 40 tokens. And then the worker can consume these tokens during that period, during that week, when it wants to basically be involved in a task. So for every regulation, we can have such tokens. So we might have a regulation that says each worker can spend 5 hours on each platform. So the registration authority generates 5 tokens per pair of worker and platforms, and send that to both platform and worker. And then when there is a task, then both platform and worker need to consume their basically their corresponding tokens. So this is how it works. So we have these lightweight, single-use, and anonymous tokens. So this token-based system is the base of verifiability that we have. So we have, and it has 5 different functions. We have generate function that is initialize the budgets and refill them, and it is by the registration authority. We have a spend function that basically different participants can spend their tokens. We have a proof function. This proof is needed for verifiable regulations. You remember, verifiable regulations are the one that are like saying that a worker can work at least 10 hours. The worker needs to work at least 10 hours a week. So you need to prove that you have worked at least 10 hours. So you need this proof function to say that, okay, I have worked at least 10 hours, and these are the 10 tokens that I have used. And we have check and alert if something went wrong, or if there is some to report some malicious spending. So if we take a look at the SEPAR architecture, we can see that each platform is basically implemented as a permission blockchain. We have nodes where we implement on, like, let's assume there are 3f+1 nodes to ensure that even if we have f malicious failure, then as we have seen earlier, then we can guarantee safety and liveness. We can guarantee safety and liveness in the synchronous basically periods. And then we have a blockchain ledger that we're going to talk about later. And you see that basically each platform is like this. So we have blockchain ledger, which is replicated on every node, and we have maybe 3f+1 nodes. You might say that, okay, we might have like 2f+1 nodes on some platforms if the nodes follow a crash failure mode. And we have the registration authority that registers participants and send them the request, the tokens, and so on. So this slide presents the execution sequence of SEPAR. So first of all, we have 2 different types of tasks, internal and cross-platform tasks. Internal means the requester sends its request to a single platform, and cross-platform task means the requester sends its request to multiple platforms. So in the initialization phase, the registration authority sends tokens to worker, requester, and platforms. Then we have publication, where the requester sends a task to the platform to either a single or multiple platform. And the platform sends a submission transaction to the blockchain, again, to either the single blockchain or all involved, to the blockchain of all involved platforms, depending on the task, either it's internal or cross-platform. And then platforms will inform workers that there is some tasks, so you can send your contribution. Workers send contribution intent messages to the platforms. Now platforms send claim transaction to the blockchain. Again, if it is internal transaction, the claim transaction will be appended to a single blockchain. If it is a cross-platform transaction, the claim transaction needs to be appended to multiple, to all involved blockchains. And then once the claim transaction is committed to the blockchain, the platform sends requests for tokens, collects all tokens, sends requests for signatures, collects basically group signatures, and put all of them to a verification transaction, and basically post that verification transaction to the blockchain of all platforms. Note that this verification transaction needs to be appended to the blockchain of all platforms. Why? Because the goal of the verifiability is to enable all platforms to check whether these constraints, these regulations are basically satisfied or not. And these regulations are modeled using these tokens. And these tokens are within this verification transaction. So when we append this verification transaction to the blockchain of all platforms, from now every platform can check whether these tokens are consumed in a right way or not. So that's why verification transaction needs to be appended to the blockchain ledger of every platform. And then everyone can check that. And at the end, we have the execution where basically the exchange of contribution and reward between involved party is done. So the blockchain ledger, if you see the blockchain ledger, we can have like different platforms in different colors. Each platform has a task submission T, and then each task has maybe one, or like this task has 3 contributions, C1, C2, C3, and each task has a verification transaction. So task might be internal or might be cross-platform task. So this is a cross-platform task between these 2 platforms, and it needs a contribution and it needs a verification. So each task has a task submission, 1 or several contributions, and 1 verification. However, what is maintained on different platforms is a linear chain, including the internal tasks, internal transactions of each basically platform, the basically cross-platform transactions that the platform is involved in them, and all verification transactions of the system. So, for example, this yellow one maintains all these yellows, maintains all these 3 because it is involved in these, and maintains all these verification, all these V's. Why? Because it needs to be able to verify other transactions, other tokens, other transactions that are processed in the entire system. So we had this blockchain ledger. We need to talk about consensus. We have local consensus, which is pluggable and depends on the failure model of nodes. We have a cross-platform consensus, which is needed among the involved platform, and we have global consensus, which requires the participation of all platforms. So if you remember, we had three types of transactions: submission transaction, claim transaction, and verification transaction. And we had two types of tasks: internal task and cross-platform task. For a submission and claim transaction, if the task is internal, we need local consensus because it is within a platform. If a task is cross-platform, we need a cross-platform consensus among the involved platform. However, for verification transaction, independent of the type of the task, whether it is internal or cross-platform, we need global consensus. Why? Again, because we need to enable all platforms to verify that the tokens have been consumed in a right way. Why? Because tokens are the regulation. Tokens are basically the way we model the regulation. So the cross-platform consensus that is used by SEPAR is a Byzantine fault-tolerant protocol because we assume that platforms do not trust each other. And basically, since it is a Byzantine fault-tolerant protocol, we have like an score message passing in accept and commit phase. And in each phase, we need agreement from the local majority of all involved platforms. And what is the local majority? It is the required number of matching replies from nodes of a platform. If nodes of the platform are Byzantine nodes, then we require like 2f+1 out of 3f+1. If they are cache only, we need f+1 out of 2f+1. Similarly, for global consensus, which is needed for verification transactions of all tasks, again, it is a Byzantine fault-tolerant protocols, again, because of the trust issue. And again, we need agreement from local majority of 2/3 of the platform. So it is, again, all-to-all communication, all-to-all communication. And the difference is in cross-platform consensus, we need agreement from all involved platforms because because there is a task, there is a transaction that is going to be appended to all involved platform, and the order is important for all of them. But here there is a verification that needs to be appended to all platforms, but the order on each single platform is not important. So we need local majority of 2/3, not all of the platforms. So if we receive local majority from, for example, 3 of these platforms, then it is enough. We don't need to wait for local majority of P1, P2, P3, and P4. If we receive local majority of 2/3 of them, we can assume that, okay, 2/3 of them agree with that and go to the next step. So one problem with SEPAR is it needs a centralized registration authority to basically model these tokens. So we are going to introduce Quorum, which is another like permission blockchain. It is not in the context of crowd working environment. It is more in the context of financial transaction, but it is basically used for verifiability, and it doesn't need that centralized modeling of tokens. So Quorum is a permission version of Ethereum. It has a shared blockchain where basically we have a single shared complete blockchain of transaction. So you remember in SEPAR, we different enterprises, different platforms maintain different views of blockchains. So the blockchains of different platforms were different. But here we have a single shared complete blockchain, and this blockchain is validated by every node, and it maintains all public and private smart contracts, or basically public and private transactions. So we have two types of transactions, public and private, and all of them are maintained in these shared blockchains. So we have a network in the basically underlying network where these private smart contracts are basically transmitted point to point, and the relevant parties. So if we have some smart contract that is between like 2-3 nodes, 2-3 parties, only those 3 parties are involved in that smart contract, and then the hash of that basically smart contract, private contract, is stored on the shared blockchain. So we have a shared blockchain that includes public transactions or public smart contracts and hashes or encrypted private contracts. So everyone can see that there are some contracts that are encrypted, and only the nodes who are involved in that contract can decrypt the contract and basically execute the transaction. So in Quorum, verifiability is basically guarantees using zero knowledge proof. So we can say that Quorum enables transferring of digital assets on a distributed ledger without revealing information about the sender, receiver, and quantity of assets. So it uses zero knowledge proof, and it uses the same technique as Zcash. So if we assume that it's a transaction in Bitcoin, so if we have a transaction in Bitcoin, we know that okay, this is the input, and the input is it is signed by like Alice, or it is signed by like a public key, and there is a transaction by this input and output. This is the quantity of output, and again we have input and output for the second transaction, and this is going to be another address which is signed for Bob or Charlie. So these are different addresses, and these are different quantities. But in Zcash, if we show that in a very simple way, we don't know the quantity and we don't know what are the addresses. So this is the way that it is privacy preserving manner. It is, but it is verifiable. We can verify that this transaction is correct. We want to conclude our verifiability discussion in this slide. We have introduced two techniques. One is token-based, which is in SEPR, used in SEPR, and one is cryptographic techniques, basically zero knowledge proofs, which is used in Quorum. There is actually another technique, secure multi-party computation, which is used on top of Hyperledger Fabric, which we haven't introduced in this part. Token-based techniques require a trusted centralized authority to generate tokens. But on the other hand, SEPR doesn't need to replicate our transactions on every node, resulting in improved performance. Cryptographic techniques, on the other hand, are decentralized, and there is no need for a trusted entity. However, they have considerable overhead, and if the system has many local transactions, since we need to replicate all transactions, we need to replicate the entire ledger on every node, using such techniques are not beneficial.